So welcome back, Gen Chem friends. Good to be with you again. So we are finally ready to talk in more detail about metathesis reactions, also known as double displacement reactions. We introduced that concept in the very first video for this chapter. We said that let me get my little pen here. We said that double displacement reactions are those reactions where you have two ionic compounds, let's call them A, B, and for CD. You have two ionic compounds, and in that metathesis or double displacement reaction, everyone switches partners. So the cation from one species gets paired with the anion of the other species and vice versa. So generically, a double displacement reaction is AB plus CD to give you AD plus CB. Always putting the cation first and the anion second. What we're going to focus on now are double displacement or metathesis reactions that are precipitation reactions. And we said that precipitation reactions, those are obviously double displacement reactions where one of the products is insoluble or a solid. So let's introduce the precipitation reactions again, and let's talk about how to predict a double displacement precipitation, how to predict the products for a double displacement reaction. So let's say you have two reactants, which we have here, lead 2 nitrate and potassium iodide. Both are aqueous solutions. And I know I've already got the products written here, but let's talk about how to determine the identity of those products as well as their states, and then we'll balance the equation. Let's say I was to give you these two reactants and ask you to predict the products. Hopefully you'd say, oh, I've got two aqueous compounds that are ionic. So this is going to be a double displacement reaction where the cation of one gets paired with the anion of the other. And so in the previous example I showed you, I just drew arrows to kind of show the switch, but I really like doing this little crisscross technique so you can clearly see which ion is being paired with what, and also with regards to balancing charge. So for my first reactant, the lead 2 nitrate, my cation is lead Pb, and that lead, remembering from chapter unit 1, that lead is a transition metal that can form more than one charge. Looking at the balanced chemical formula, I see, oh, it's paired with nitrate, that polyatomic anion, NO3, and each nitrate that you memorized, nitrate has a -1 charge. Since there's two of them, that means my lead must be a +2 in that compound. So on this top line here, I've made this little crisscross and I've put the cation and the anion for my first ionic compound. And I'm going to do something similar with my second ionic compound, the potassium iodide. My cation is potassium, which is a +1 charge. My anion is iodide, which is a -1 charge. And so now it's a little more clear, hopefully, to determine which cation gets paired with which anion. So I can see that the lead is going to be paired with the iodide, which is what we've done down here. And since each lead is a +2, the only way that my charge of my molecule can equal 0 is if I have two iodides. Remember, when putting ions together to make a neutral molecule, always subscripts. So PbI2. We'll talk about how to determine states in a second. My second product is going to be the potassium paired with the nitrate. And since potassium is a +1 and nitrate is a -1, I just need one of each. So KNO3. So that's how you predict the products of a double displacement reaction. The states are determined by using the solubility rules and looking to see where that molecule falls on those solubility rules. We said that lead to iodide, it's one of those exceptions for iodides. It is insoluble. Potassium nitrate, all nitrates are soluble according to the solubility rules, which you will have for the exam. Things that are soluble are AQ or aqueous. Species that are insoluble are S or solid. And so now the only thing that's left to do with this reaction is to balance it. And remembering, when you balance a chemical equation, it's always coefficients, numbers in front of each species. I immediately see that, oh, I've got two NO3 chunks, two NO3 ions. On my product side, I just have one, so I need to put a 2 in front of the KNO3. So now my nitrates are balanced, but my potassiums, I've got two potassiums now on my product side, so I better put a 2 in front of that Ki. And that works out great because that also balances our iodides. And each lead is also balanced. We have one lead on the reactant side and one lead on the product side. So that is our balanced equation for this reaction. We were able to predict the products doing this little crisscross for the double displacement. The cation of one gets paired with the anion of the other, making sure that when we put ions together, the overall charge of that molecule is 0. Then determining states from the solubility rules, and then balancing by the equation by using coefficients. So in the next video, we're going to do another example in predicting the products and balancing a double displacement reaction. And then we'll talk about how to use that double displacement molecular equation. And this equation is a molecular equation because all of my species are molecules. We're going to talk about how to use a double displacement molecular equation to write something called the total ionic and the net ionic equation.